table your A, B, C.
Okay, which one did you make A?
I made R, A.
Okay.
And I made 12, B.
Okay.
And 13, C.
Excellent.
So then I did A squared plus B squared equals C squared. So R squared plus 12 squared equals 18 squared. I'm sorry, 13 squared.
13 squared. Okay.
And then I squared it, so R squared plus 144
Uh-huh.
equals 169.
Yep.
Subtracted the 144 to the side. And I got R squared equals 25.
R squared equals 25.
Yep.
Okay.
Square rooted it.
Take the square root. Yep.
I made it R equals 5.
Guys, give it up for Kristen. Beautiful. Okay, very nicely done. Guys, we are changing gears a little bit in this chapter, but this is a very important problem. These right triangles are going to show up again, okay? Now, in the second one, we had two sides that were R. So we can't use the Pythagorean theorem for the second one. What's that? Use sine. Do you know either of the angles? Do we?
No, you don't.
Do we?
Oh, really?
They're both 45. Why do both of the angles have to be 45 degrees?
190 and R is the same.
It's an isosceles right triangle. So now you could have used sine for this one. Sine of 45 would have been R over 18. You could have also used 45, 45, 90 rules, right? That would make R little a. That would make this R little a. And that would make the 18. Who remembers 45, 45, 90 rules? A times the square root of 2. So the one that we were given was the hypotenuse, which is the 18. So let's solve 18 equals A times the square root of 2. Let's solve that for A. What would we have to do? What do we have to do for this? I want to solve this equation. Do not square both sides. Because remember, we would only square both sides if the A was underneath the radical. Not divide by 18. You are going to divide though. Dougie?
So you would divide A times the square root of 2 equals 8. Well, it's like you do A times the square root of 2 equals 18, and then you divide both sides by the square root of 2.
Excellent. Divide both sides by the square root of 2. Good job, Dougie. Okay? Because now these square roots of 2 will cancel. Because it was A times the square root of 2. We undo multiplication with division. So now we have A equals 18 divided by the square root of 2. And if you plug that into your calculator, let's see what we get. 18 divided by the square root of 2. I got 12.7. Okay? Did anyone do it a different way? Yeah. You did the Pythagorean theorem? Okay. Hey, I want us to pay attention because Anja did it a different way, and this is also correct. How'd you set it up, Anja? Why did you set it up like that? Very good. These are my two legs. My a squared plus my b squared should be equal to my c squared. Okay, what'd you do after that? 324. Okay. What's r squared plus r squared? No, it's not r to the fourth power. You didn't do that.
No, I just knew to divide it by 2.
Ah. So let's see why. Remember, r squared plus r squared, do you agree that's 2r squared? So now when we divide by 2, Anja, this makes sense now. 324 divided by 2 is 162. So we have r squared equals 162. What do you think we're going to get when we take the square root of both sides? 12.7. So r is equal to 12.7. Okay? You get the same answer regardless of how you do it, guys. Okay? Feel free to use either method. Go ahead. Make sure you set a timer, okay? Grayson, put it away. Yes. right, guys, so we're going to start today with lesson 10.1, okay? This involves a new geometric shape, which is called a circle, okay? So the first thing that I want you guys to do is I want you guys to go ahead and I want you to look at all of these 5 different vocabulary words, and they're labeled on the circle on the right, okay? There's a chord, there's a secant, there's a tangent, there's a radius, and there's a diameter. We will talk in more depth about each one of these, but right now I want you guys to kind of not guess, but like do your best to write down a small definition next to each one, okay? We'll do one together. So let's look at the chord. So find the chord on the diagram. Do you guys see the chord? What do you notice about the chord? It's a straight line. Okay, so it's a straight line. Does it end? Okay, so it ends. Where does it end?
On the other side of the circle.
On 2 edges of the circle. Okay, so it ends at the edge of the circle. What else can we say about the chord?
It's placed on the top.
It's kind of like on the top, right? It's not going through what?
The diameter.
The middle, okay? It's not going through the middle. So I want you guys to do that same thing for each of these. I want you to write your personal definition for each one, and let's see how close you get to the actual formal definition. So go ahead and try that. Do the next 4, go. Tell me what they think a secant is. A secant.
I got a circle.
What is it, John?
It's like the chord, but it keeps passing through the line.
Excellent. It's a chord that extends past the circle. So it's a chord that's a line, okay? Please make some sort of note that a chord, we said it was a straight line, right? But it's actually a straight line segment, okay? Because segments, remember, end on both ends. Do you guys agree? Lines continue on forever. So the only difference between a chord and a secant is that one's a line and one's a segment. A chord will be a segment, a secant will be a line. Do you guys see that? Okay. How would you describe a tangent? Go ahead.
9 degrees and it runs like touching the outside.
Very good, Zach. There's a 90-degree angle, but with what? It forms a 90-degree angle with what? Good. 90 degrees with diameter. And you said what about it? What was the second thing?
It touches the outside.
Excellent. It touches the circle at one point. Okay? That says it touches the circle at one point. A chord and a secant touch the circle at how many points? 2. Okay? The tangent is different because it only touches the circle at one point, and it's this point right here. Okay? How would you describe a radius? How would you describe a radius? Go ahead, Hannah. Say it one more time. 180 degrees with the diameter. Oh, okay. So if you took a radius and you extended it 180 degrees, then it would become a diameter. Yeah, Kristen?
I said that it's a line segment that meets in the middle.
Excellent. It's also a segment, okay? And you said it meets in the middle? Very good. It's one endpoint is in the middle. Where's the other endpoint?
Touching the outside.
On the outside of the circle, okay? So one, and then the other one is meets in the middle and the edge of circle. I'll just put and the edge, okay? We'll call that the edge of the circle. And then what did you say, Grayson, about it?
It's just half of the diameter.
It's half of the diameter. Perfect, okay? Let's write that over here on the left. It's 1/2 the diameter. Okay? So if my diameter was 10 units, how much would my radius be? 5. You just divide it by 2. And if my radius was 3 for a different circle, how much would my diameter be?
1.5.
No. 6. So if you're given the radius, multiply it by 2 to get the diameter. If you're given the diameter, divide it by 2 to get the radius. All right, and then how would you describe a diameter? Go ahead, Cody. Cuts the circle in half. Okay, and it is a segment. Very good. Now, I'm going to update this definition for diameter. Do you agree that it is a chord? But what's so special about the chord? It passes through the middle. Okay? So the diameter is a chord, okay? It is a segment that goes from one edge of the circle to the other, but it must pass through the center of the circle. Yes? Yes, it absolutely does cut the circle in half. That's exactly what Cody said too, okay? Both of those are correct. Diameters will always cut your circle directly in half. Good job, okay? What questions do we have about this first slide, guys? Christian, was that a hand? No? Okay, so the reason I do this is because I like you guys to think about these definitions before we talk about them formally. Now, the rest of the slides is just taking all this information and putting it into a concise definition. So, that I put on my figure, this point is our point of tangency. I'm going to put POT, okay? It's wherever your tangent touches the circle, okay? Just so you guys have a visual of it. On the next slide, it says we have 3 different definitions. We have the definition of a circle, what the center of a circle is, and what a radius is, okay? A circle is the set of all points in a plane that are equidistant from a given point in that plane. Go ahead and copy down that definition. And then I want us to actually draw it out. Okay, so how I want to describe what a circle is, okay, is I want you to start, and I want you over on the right side of your notes, I want you to draw just a dot, okay? A singular dot. Now, in Notability, you guys are going to be able to draw a circle around that dot and hold it once you reach the other end of the circle, okay? So draw a full circle around that dot and hold it. I can't because I'm not using Notability, but if you guys hold it, it will create a perfect circle, okay? I want you to line that circle up so it's the same distance everywhere from the middle of the circle. So I'm going to try to do mine a little bit better. Wow, that's pretty good. So this is by definition what a circle is. It says that all of the points on the circle are the same distance from that point in the middle. Do you guys agree? If you drew it good enough, okay? Or well enough. Now, the center, what we call the center, is that point. So that center, draw an arrow to the middle of that circle. That is what we are going to be calling the center of the circle, okay? So that point in the middle, that is your center. And then the radius, okay, use a different color here, is the distance from that center to any edge of the circle. And there are infinitely many radii, okay, in this circle. So it doesn't matter which one you draw. You could have drawn one that looks like this. You could have drawn one that looks like this. They're all radii as long as they start in the middle of the circle and they go to an edge. Now you're going to hear me say the word radii. Radii is just the plural of radius because you don't say radiuses, okay? You don't say radiuses, I know. What? I don't know, it's just not what we say. I guess it's not a word. Radii is the plural of radius. What questions do we have for me so far? Go ahead. The what? The black is the radii, correct. All 3 of those are different radii, but they're all going to be the same length, okay? Good question. Any other questions? What questions do we have? Okay. Oh, yes. So the next 3 we're going to talk about are the formal definitions, for our chord, secant, diameter, and tangent. A chord is a segment whose endpoints are on the circle, okay? A diameter is a chord, but also contains the center of the circle, so it must pass through the middle. A secant is a line. Underline the word line, guys, okay? A secant is a line, not a segment, that intersects a circle in 2 points. And then a tangent is a line in the plane of a circle that intersects the circle in exactly 1 point, called the point of tangency, okay? Now, if you guys go back to the first slide, that blue point that I put on my... So that point is a point of tangency. And tangent lines only have 1 point of tangency with their circle, okay? What questions do we have on this slide? Okay, I'll give you another minute. If you're done, take a look at the next 2 questions on the next slide and see if you can answer those on your own. Yes, you may. Make sure you set a timer. Sorry. I want you to answer are all chords diameters? Are all diameters chords? Then I want you to think, why do you think we have to state that a tangent is in the same plane as a circle? And to answer that second one, I want you to think, what if they weren't in the same plane? Okay? So answer both of those. I'll give you about 1 minute, and then we're going to discuss. Go. All right. Let's talk about it. Are all chords diameters? No. Why not? Diameter has to go through the middle. Can a chord be a diameter, though? Yes, but it has to do what? Go through the middle. But all chords do not necessarily have to go through the middle. Do you guys agree? Now, are all diameters chords? This is yes, okay? Because in order to be a diameter, do you agree that both ends need to be on the edge of the circle? And that's all a chord needs, okay? Now, the second one. Does anyone think they know why we need to state that a tangent must be in the same plane as a circle? Because it's 90 degrees? Yes, that's part of it. It is not half of it. Hayden? It does have to touch the circle. How I explain this one, and I want you guys to do this as well, draw a circle on your, right at the bottom here, okay? And I need your eyeballs up on the screen because I'm going to walk you through it. Let's imagine that my arm is a line. Is my arm currently tangent to the circle? Yes. Yeah. Is my arm now tangent to the circle? No. No, because it's going to pass through twice. What about over here? Yes. What's this? Is my arm tangent to the circle? No. Are you sure? Yes. How many times does my arm touch the circle? Once. But is my arm in the same plane as the circle? Yes. Oh. Are you sure? Yeah. Is my arm still tangent to the circle? No. It sure is. It's only touching one time. Do you see how more complicated it becomes once I extend it off the same plane? Do you guys agree that the circle exists on the plane of the projector, correct? And as soon as I was like this, you guys were all like, yeah, it's totally tangent. Yeah, it's totally tangent. And then we're all like, I don't really know. So what we're going to do is we are going to only think about the plane of the circle. Yes, go ahead. Okay? So we're only going to think about the plane of the circle, okay? Because otherwise, there would be a bunch of different lines in other planes that are also tangent to that circle, okay? So we are only going to recognize the plane of the circle. Okay? Because otherwise, you get all these other lines that could be touching your circle at one point, but not necessarily tangent to the circle, and not necessarily forming a 90-degree angle with the diameter or the radius. All right, this next slide, guys, it's the same exact slide from that first one, but I just added in where I pointed out the point of tangency, okay? It's the point where the tangent line touches the circle, okay? Go ahead.
Write those down.
No, are they not filled in for you? They're blank? Oh, okay, then yeah, go ahead and copy them down. So the top one is a chord. The middle one is a diameter. The one towards the bottom is a secant, and the one at the very bottom is your tangent line. And then that's your point of tangency on the tangent line. If I were to also fill in the center of the circle, where would it go? On the diameter, very good. It would need to be somewhere like right here, okay? And you're going to see a lot of the times that point in the circle is going to be labeled something. Let's label it D, okay? So now you're going to see this notation now for circles. If we want to identify this circle, we would use the circle symbol, which is a circle with a dot in the middle, and then you label it by its center point. What did we say its center point was?
Diameter.
D, okay? So we would call it circle D, okay? This is the notation for calling out this circle. Bless you. All right. So point O is the center of the circle. Name each of these in the figure. Okay, let's do this one together. You may want to extend the point on O just so it intersects in the intersection. Okay. What would we call OM? It would be a radius. Very good. Why is it a radius? It's from the middle, the center of the circle, to the edge. Do you guys agree? That is a radius. Very good, Kristen. What about MN? Someone else.
Chord.
Why is it a chord? Who said chord? Why'd you say chord, Zach?
Because it's on the top and it goes through.
Very good. And it's also a line or segment? Segment, because of the notation. Do you guys see that? Now, MN is also used for C, but it's not a chord anymore. Why did it change? Grayson?
Because it's not a segment anymore, it's an actual line.
It's an actual line. So what do we call it now?
Secant.
This is a secant. Very good. Okay. When you add those arrowheads on top of the MN, it becomes a secant. What about MQ? That's a diameter. Very good. Is it also a chord? Yes, but I would expect you to label this diameter because I want you to be as specific as possible. Okay. What about ML? Very good. It's a tangent. Now, remember, tangents have to be lines. Is this a line? Is it a line? No, it's a segment. So we can't just label it tangent. We have to be specific. We have to say it's a tangent segment. Okay? We have to say it's a tangent segment. Now, tangents can be segments, rays, or lines. The only one that's a true tangent with nothing afterwards is if it was a tangent line. For example, letter F. ML as a line is just our tangent, okay? We don't need to say it's a tangent line. If you do, it's fine. It's not going to be wrong. But just make sure you specify if it's a segment or a ray, okay? What would we call point M? It is not the center and it's not the tangent. It's the point of tangency, okay? What questions do we have? Yeah, talk to me. Yeah, that's fine. Mm-hmm. What questions do we have? Yeah, Scott. Yeah, set a timer. Okay. Now, the next thing we're going to talk about are common internal versus common external tangent lines, okay? Now, they're very, very easy. A common internal versus a common external involves two circles, okay? So as you'll notice in the diagram, how many circles do we have in each of these? Two here and two here, okay? So what you do is you draw a segment from one circle to the next, right? So go ahead, use a different color other than black, and draw the centers of each of these two circles. I know it's a common tangent because do you guys agree that that black line is tangent to both circles? Do you guys agree it's tangent to both circles?
Yes.
Cool. Now draw the line between the two centers of the circles. If the line that you drew crosses the tangent line, it's an internal tangent. If it doesn't cross, it's an external tangent. Do these two lines cross?
No.
They don't cross or don't intersect. Correct. So if they don't intersect, we say it's external, okay? It's external. So this is an external common tangent. Okay? Now we do the same thing for the second one. What do you think this one's going to be? Internal. Because if we draw our two centers and we draw it across, do you guys agree they intersect right here? So in this case, they do intersect. So we would say it's an internal tangent.
Pardon the interruption. Marco Sanchez, please report to student services. Marco Sanchez, please report to student services. Thank you.
Okay. How we feeling? What questions do we have right now? Yes.
So for the one on the left, is that like a segment or a line? Because I thought the tangent had to be a line.
You're absolutely correct. So we should be, it is considered a tangent, but they should be more specific and say it's a tangent segment. If you want, just so we're clear, you can go ahead and put arrowheads on the edge of that so that.
Oh, because the other one's a segment, so it wouldn't
Correct.
cross anyways.
Okay? Good question. What other questions do we have? Okay, so next thing we're going to talk about is the difference between congruent and concentric circles, okay? Congruent circles are circles that have congruent radii. How I want you guys to point this one out is I want you to draw the radius of the inside circle and give it a segment mark so you know it's that distance long. Then draw a similar sized circle over here and give it the same length for the radius. Congruent circles are the exact same size. That means that their radiuses, or radii, need to be the same length. So if this radius was 3 units and this radius was 3, would you agree both of those smaller circles are the same size, they're congruent? Correct, okay? Congruent circles, they don't need to be overlapping, they don't need to touch, they just need to be the same size. They have the congruent radii. Concentric circles are circles that lie in the same plane and they have the same center. So for example, do you see the two circles on the right-hand side? Do you agree that they both share the same center?
Yes.
These two circles, although they're not the same size, they are concentric, okay? Now, are those two circles congruent?
No.
The answer is no. Why not?
Different sizes.
They're different sizes. Very good, okay? So you can be concentric and not congruent. Can you be both? Congruent and concentric? You sure can, but what would be the case if they were both congruent and concentric? It would be overlapping. It would be the exact same circle twice. Okay? All right. Tangent circles. So, coplanar circles, that means they lie in the same plane, that are tangent to the same line at the same point. In other words, the two circles are going to touch at exactly one point. Okay? You see an example on the left where they're just touching on the outside, and you see an example on the right where they're literally one's inside of the other one and they touch on the very edge of the circle. Okay? What do we call this point where they do touch?
External.
Nope. The point of tangency. Very good. Okay? We call that point the point of tangency. Now, let's do it. So let's determine whether it's an internal versus an external common tangent. Draw the two centers of these two circles and draw the line connecting them. Does it cross over the tangent line?
Yes.
So we would say it's internal or external? Internal, very good. Do the same thing for the second one. Center's right here, center's right here. Draw your line. Do the lines cross?
No.
No, so what do we call it? External. Okay? That way we can all study these definitions. All right. We already touched on this, but we're just putting it into a theorem. It's the tangent line to circle theorem. It says in a plane, a line is tangent to a circle if and only if it is perpendicular to a radius of the circle at the point of tangency. Okay? So basically, any tangent line is going to be perpendicular to the radius, and that is the tangent line to circle theorem. Now, it is an if and only if statement. That means it works both ways. So that means if you know it's perpendicular, it has to be a tangent. If you know that it's a radius and a tangent line, then you know it must be perpendicular. Okay? All right, and then the external tangent congruence theorem. Guys, just as a little side note, I like to explain this one as an ice cream cone. Okay? What this theorem says is it says the tangent segments from a common external point. The common external point here is point B. Those must be congruent. So the distance from B to the point of tangency A is the same distance from B to the point of tangency C. Okay? Now, why I compare this to an ice cream cone, imagine that AB and BC are the segments of an ice cream cone, right? Kind of like making a V. Your ice cream, if those two segments were not the same length, your ice cream would fall out of the cone. Do you guys agree? So by this theorem, it says that those two segments need to be the same length for your ice cream to hold inside the cone, okay? So if you think about it as like, if you were to redraw the same picture, like this, these two need to be the same length so your ice cream doesn't fall to one side or the other, or it doesn't start to drip off the cone, right?
Yeah.
So that's how I like to think about it. I always compare it to like the ice cream cone theorem, okay? Now, you cannot say it's the ice cream cone theorem on an exam. You have to know that it's the external tangent congruence theorem, okay? All right. Now we get to the examples, the fun part, okay? We're going to jump over back to this slide where it's talking about is ST tangent to the circle P. Okay? You should have seen some of these on your homework, okay? Let's talk about what we're supposed to do here. In order for ST, guys, I went back a few slides. This is slide number 15 out of the whole thing, okay? In order for ST to be tangent to the circle, what does this angle have to be? 90 degrees, very good. So let's assume that it is tangent, right? Let's make that a 90 degrees. If this is a right triangle, it has to satisfy the Pythagorean theorem. Do you guys agree? Let's see if it satisfies the Pythagorean theorem. Someone set up what the Pythagorean theorem would be for these three sides. Go ahead, Cody. Uh-huh. Excellent. Now, Cody, if the left side equals the right side, we know it's a right triangle. We know it has to be tangent. If it's not, we then know, okay, this line is not tangent to the circle. Okay, let's test it out. 12 squared is 144. 35 squared is 1,225.
Well, that's 35. I think. Am I going crazy? Yeah, I'm going crazy.
And then 37 squared. What were you saying, Dinah?
No, I'm going crazy.
1369. So then we add 1225 plus 144. 1369 equals 1369. So we know ST is tangent to circle P. Hmm? What's up, Johnny?
Why is 37 the C here?
Why is 37 the C? Okay, so Ronnie, when you draw your right angle, right, you've got to draw it in there so that you can see, okay, that's the side that's opposite my right angle. That has to be my hypotenuse. Does that make sense? So sometimes, Ronnie, we may see it where it's like down here and like this, right? And the right angle's over here. 37 is still going to be your hypotenuse, okay? Good question. And what other questions do we have on this example? Okay. Guys, so go back. In example 2, guys, this is a really good one where we can practice what we just did. I did 2 examples with you in the homework, and I did one on the warm-up. I want you guys to try this problem, okay? Use the Pythagorean theorem. Try to set this one up and solve on your own. Go. So, what do I start by setting up? Because I have to use the Pythagorean theorem here. What are my 2 legs? Cody? Oh, what's your question? Why don't I multiply 39 by 2? It wanted the radius, right? If it wanted the diameter, then you would multiply it by 2, okay? But if it just wants the radius, just solve for r. Let's go ahead and solve this one. What are my legs, guys? 80 and r. So we're going to set up r squared plus 80 squared equals, what's the hypotenuse, peeps? 50 plus r, and then we're squaring it, okay? R squared is just going to be r squared. 80 squared is going to be 6,400. This is when you square 50 plus r, when you FOIL it out, you should get 2,500 plus 100r plus r squared. Then you subtract the r squareds from both sides. They're going to cancel. You get 6,400 equals 2,500 plus 100r. What do I do? Subtract 2,500. You get 3,900 equals 100r. Then what? Divide by 100. Divide by 100. And you get 39 equals r. Boom. What questions do we have? Zach? Oh, yes, you may go. What questions do we have on this one? We're okay? All right. I want you to go down to example 3, please. We'll go back to example 2 in a moment. All right. In example 3, it says name a line that's tangent to circle P, but not tangent to circle O. It's got to be tangent to circle P, but not tangent to circle O. What's that? OB is correct. Now, what notation does it need? Is it a line, a segment?
It's a line.
It's a line, so it needs to have arrowheads on both. Remember, it said name a line tangent. So it should be OB with arrowheads. Name the common external tangent to circle O and circle P. CD is correct. How do you know that it's external? If you were to draw a line between the 2 centers, does it cross that line? No. And then name the common internal tangent to circle O and circle P. That would be AE. Very good. Okay? Make sure that it has lines on both because we're talking about tangents. Or arrowheads on both, excuse me. What questions do we have on example 3? Are we okay? All right. How do you know if it's internal or external? Zach, go ahead.
If you see that line in the middle of Koji, what line is it?
From center to center, right? From center to center. If it crosses over that line, it's internal. If it doesn't cross that line, it's going to be external. Okay?
I just had to write that.
Yep, you got to draw that line in yourself.
How do you know if it's internal?
Wait. Okay. Example 4. Circle M and circle N are tangent at the point P. Guys, make a point at point P. PR and SR are tangents to the circle N. And circle N has a diameter of 16. PQ is 3 and RQ is 12. Let's find PM. So let's go ahead and fill in some information. First off, it told us that PQ is 3, so let's fill in a 3 there. RQ is 12. And we know that the diameter of N is how much? 16? 16.
For 16, that's diameter.
Mm-hmm. So that would mean that the radius of N is how much? 8. Very good. So we know that it's 8 and 8. Now remember, N and M are both tangent, correct? And circle M has one edge on the edge of N and one edge of its circle in the middle at N. So if we were to draw another radius here, right? We know that that radius is 8. And that's the diameter of circle M, correct? So what's the radius of circle M? 4 and 4. PM then would be the radius, right, of circle M. So it's going to be 4, okay? MQ. Now this is where it gets a little tricky, guys. MQ. I want you guys, it's not even a segment that they drew for you. So draw it in. Start at point M and draw it to Q. Now, what do you notice? There's a shape that just got formed. There's a triangle. Now, I need you guys to make this connection. That point P was a point of tangency. Do you guys agree?
Yes.
What is so special about points of tangency?
90 degrees.
They form a 90-degree angle. Very good. So this is not just any triangle, but a right triangle. So in order to figure out MQ, which is this guy right here, we can use what theorem? The Pythagorean theorem. So we're going to do a squared plus b squared equals c squared. What can I plug in for a?
4.
The 3 or the 4. Good. Let's do 3 squared plus 4 squared should equal my c squared. This is going to be 9 plus 16 equals c squared. That's 25 equals c squared. So c is equal to? C is equal to 5. So I know now that MQ is 5 units. How much time do we have? We have 2 minutes? All right, guys. We'll finish this one up tomorrow, okay? So I believe we left off where we were finding PR, okay? In this very last slide, example 4. Guys, what would be the length of PR? 15. Why? You just add 3 and 12, right? So very good. It would be 15 units. What about SR? It's also going to be 15. What theorem? Yeah, it's a congruence theorem. Specifically, external tangents congruence theorem, okay? I like to call it the ice cream cone theorem, right? So we know that this one's also 15. NS, guys. N to S. Who said 8? Cody, why? Well, let's look at the segment NS. It's not a diameter. What is NS? It's a radius, so it should be half whatever the diameter was. And Zach just said the diameter was 16, correct? So what's half of 16? 8. Bingo. Okay? All right, so now it's asking us for NR. So let's draw NR, which is this segment right here. But guys, I want to point something out to you, okay? First of all, let's erase this. Let's make this look better. It should connect to S. So let's draw N to S. It's still going to be 8, but it just looks better if it's like this. Remember, S is a point of tangency. It told us that in the instructions. If it's a point of tangency, what angle does it make with the radius? 90. So what triangle am I dealing with? Very good. It's involving a right triangle. Highlight that right triangle. We know 2 of the sides. We're missing a third. What do I do? The Pythagorean theorem. Very good. So how do I set up the Pythagorean theorem for that right triangle in the bottom here? Hayden? Very good. C squared. We'll leave it as C squared, and then we'll know whatever C is going to be the length of NR. Excellent. So 8 squared is 64 plus 225 equals C squared. I think this gives me 289 equals C squared. You take the square root of both sides, and you get 17 equals C. So the length of NR, our last length, is 17. Okay, I believe we need to go back to 2 examples previous, okay?